Hello everyone, welcome to the NN Classroom. Today I'd like to share with you a past paper question from 2019, Time Zone 1 in May, question number 9. A really typical type of question that students must know that in really great detail, especially the explanation as well, because this type of question is possible to be present in paper 2, so that is the long structural questions. Let's see, they're asking, what is the order of increasing boiling point? So simply asking for really common physical properties from topic 4, bonding and structure, asking for the comparison of boiling point or melting point. In this case, remind you that no matter boiling point or melting point, the thinking mindset is always going to be we need to think of the competitors, bonding, and structure critical, because the bonding and structure will govern to the types of attraction that we are overcoming during the process of boiling and melting. So obviously for this case, all these are going to be organic compounds, right? And no doubt organic compounds are achieving a bond type of covalent bond. So our answer in this case is covalent bond we are now focusing on. And the structures, as we know, for covalent compounds, it exists as two possibilities: either the giant covalent structures like diamond, graphite, silicon dioxide, or the majority, what we call the molecular structure. Right? So that means this is the case to be this time, right? Obviously, because all these are not the diamond form, not the graphite, but exist in a discrete unit called the molecular structure or simple molecular structure. So that's why in this case, once we determine the types of bond and types of structure, that now we should be focusing on what types of the attractions or interactions we are overcoming during the process of boiling or melting. In this case, if it is going to be the molecular structure, so obviously we are overcoming the intermolecular force. LECULL, intermolecular forces. And particularly that means now we are comparing the strength of intermolecular force, but not the bonding type. Be careful, right? Because what we are now in is all molecules. And in terms of breaking molecules in boiling or melting, we just need to overcome the intermolecular force. So now this question is now breaking down in the case of like we need to compare the strength versus the strength of intermolecular force. I simply call it IMAF, right? Yeah, makes sense. And when comparing the strength of intermolecular force in our class, we have specifically organized in the thinking mindset. So organized that we need to think of three factors, so important. And this time we are going to use just the first factor that can able for us to kill the question, and that is what we call polarity. That is the most important factor, to be the first factor that we must think of when we think of the strength of intermolecular force or compare the strength of intermolecular force, right? So that's why for this case, the higher the polarity or the greater the polarity, the stronger the intermolecular force is, because polarity helps us to classify the intermolecular force into different types, including the strongest one, which is going to be number 1, hydrogen bonds. The second one, what we call the dipole interaction. Or the third one, which is the weakest one, but everyone has it, called the London dispersion force, or simply called London forces, right? So that's why if we can classify the types of the polarity, then we can classify the types of intermolecular force, so that we can see which one is going to be stronger in terms of intermolecular force, thus having the higher boiling point or melting point, right? So in this case, first of all, we should be looking for all the homologous series. That means the families that they belongs to, right? No doubt, the first chemical, the first compound that you can see across all the choices, which is going to be an alkane, right? Alkane is something that are all saturated hydrocarbon containing just CC and CH1. And we notice that alkanes is actually having only the weakest intermolecular force of London dispersion force due to the non-polar nature of the entire compound, right? And the second candidate that we have is actually alcohol, right? With an OH group that present. And alcohol, no doubt, is a pretty strong molecule having a strong intermolecular force because of the presence of the hydroxyl group. This hydroxyl group lead to the possibility in forming hydrogen bonds between alcohol and alcohol. So that's how we should expect alcohol should be a quite strong molecule in terms of intermolecular force. And the third one, which is going to be a CO double bond present, that is going to be a ketone. Ketone, yes, is still pretty nice in terms of the intermolecular force, but can it form hydrogen bond? No. The polarity is only able for ketone to achieve the second strong one, dipole-dipole interaction. So now in our mindset, we can already rank that from the first three. We should notice that alcohol should have the strongest intermolecular force, which is hydrogen bond. Maybe I'll point it out. Hydrogen bond, right? Which is going to be pretty nice, the best one. The ketone comes second because it has the dipole-dipole interaction. Right? I just mark it here first. Right? While alkane is the weakest one because it only bears the London dispersion forces. Right? I just use the short form because not enough space. Right? So because of these three types of interaction, we can already rank alcohol should come first, followed up by ketone, and finally the alkane. Right? But let's look at the final one. This one, which is the cane. Carboxylic acid. In terms of a carboxylic acid, ClBoxylic, it is also a very polar molecule in which it should attain also the hydrogen bonding between the acid and acid molecule, right? So now you should see two of the classes or two of the homologous series, alcohol and carboxylic acid, both containing the hydrogen bonds in holding the molecules and molecules together. So that's why these two should be the champion, followed up by ketone and finally alkane. But then comparing the two champions, which one is actually better? Finally speaking, acid has one extra bonus point because of the quota. So when both molecules are able to form hydrogen bonds, which one is going to be even stronger is by looking at the quantity, because here comes the quality to be differentiating. But then if both are having the same quality of forming hydrogen bonds, strong, but then the final one should go to the one that forms more of the hydrogen bonds. As we can see, carboxylic acid is having more of the groups that are able to donate hydrogen bonds or receive hydrogen bonds. But for alcohols, there's only one oxygen and one hydrogen compared to two oxygens and one hydrogen in the case of carboxylic acid. So that means in terms of number of hydrogen bonds per molecule, acid is going to be having a bigger number than alcohol. So this is the extra point that students should know, and that actually differentiates why carboxylic acid is the champions of the champions when comparing to the alcohol. So that's what the correct order is. We should choose carboxylic acid to be the first, followed by alcohol comes second, and finally ketone as the second type of intermolecular force, a weaker one, only the dipole-dipole interaction. And finally, the weakest one goes to only London dispersion force, and that's for alkane. Right? So that's how the right order will then be for B.